Bonding and electronegativity. So remember, we have two types of compounds that we've talked about, and again, compound being made up of more than one type of atom. They can combine as molecules, or they could combine as ionic compounds, as depicted here. We have our ionic compound on the left, and remember, it's the formula unit that makes up what we see for this compound here. It is a ratio. The lowest whole number ratio is how we express it. So again, if it is sodium chloride, there is one sodium ion and one chloride ion. Do not forget that these are charged, though we do not include that in the actual formula. It's an ionic compound. It's made of ions. And it is not that there is one sodium and one chloride ion. There are 1 gazillion sodium ions for every 1 gazillion chloride ions. It's a 1-to-1 ratio. So that's what we have for ionic compounds. With molecules, though, they do form distinct units. So for something like H2O, you do actually have 2 hydrogens and 1 oxygen, and that makes up 1 molecule of water, and it goes around acting like water acts. But with sodium chloride, you don't have 1 sodium and 1 chloride. You have 1 gazillion sodium ions and 1 gazillion chloride ions. It is the ratio. The formula represents the formula unit. Luckily for molecules, the formula actually is how the particles themselves end up looking. Now, what we're going to be looking at today is how do you determine which of these two the compound that you're dealing with is going to behave like. And so to do that, we're going to be talking about this concept of electronegativity. So electronegativity is the ability of an atom to attract electrons specifically in a bond, not just an atom sitting by itself, because that is electron affinity, and that's not particularly useful for us. But what is really useful is electronegativity. So if you take that atom, let's say X, and you want to bind it to atom Z, they are going to have different electronegativities in that one of them may want electrons more. So they might end up forming a bond between them, but one of those atoms may hog the electrons more than the other one. So they can end up pulling on the electrons, and we can determine this by calculating out what the electronegativity difference is between these two. Who wants the electrons more? These values are on the chart here. We'll talk about trends at the end, but this is essentially, these numbers here are the electronegativity values for the atoms that we have here. So our periodic table. Again, if you want, you can think of hydrogen as being over there. But if you notice, you can see a pattern here that we should be able to explain by the end of this. But each atom has its own electronegativity value, and that essentially represents that if these atoms were to bond, or when they're in a bond, this is how much they want, or they're going to pull on or hog the electrons within that bond. And it's the difference between their electronegativity and the thing they're bonding to's electronegativity that will determine what sort of compounds you end up forming. So the type of bond that you're going to get between atoms, and then that will determine the type of compound you have. It is all determined by the difference in electronegativity. So we use this delta sign, meaning the difference in electronegativity. So we're going to look at 2 atoms at a time, and we're going to look at the difference in their electronegativities, and that will tell us about the bond that's going to be between them. We get this difference by taking the higher electronegativity value, whichever one has the higher one, and we subtract from it the lower one because we want to find the difference. That's how you do it mathematically. And that will give us the delta En, and then we'll see what that means in a minute. But let's try this with a Lewis dot diagram for the molecule. So these are 2 non-metals, so I'm going to assume it's going to be a molecule, and I'm going to be drawing the Lewis dot diagram for them and then calculating the electronegativity difference. So we have our nitrogen in the middle, and you look at which column it's in. It's in column 15, so we're going to have 5 valence electrons around it. And we have our bromine in column 17, so it's going to have 7 valence electrons around it. And in order to make them stable, they're going to be sharing their pair of electrons, which we don't want to draw like that. Instead, we want to draw with a bond, a line representing the 2 shared pair of electrons. It's going to be the same. We have the formula as Br3, so we know that there's going to be 3 of these ones. And it's going to be the same thing for each one of these. A bit of a shortcut. Again, circle, replace that with the line that represents the shared pair, and we're going to end up with the same thing happening on this side as well. Shared pair of electrons, which we represent with a line as a bond. So there's a Lewis dot diagram for NBr3. Now, we've done that before. What we want to do this time is we want to calculate the delta En for this compound. So we look at the electronegativity of nitrogen and the electronegativity of bromine, and realize that depending on which periodic table you're looking at, they may vary slightly. So if you're not getting the exact same ones as mine, that's fine. Use whichever ones you happen to have. It won't be a terribly large difference, but the periodic table I'm looking at gives me the electronegativity for nitrogen at 3.0 and that of bromine at 2.8. So then obviously the difference between those would be 0.2. So what that means is that the electronegativity for this bond right here would be, the difference would be 0.2. And it would also be, I could do the math again if I want to, but it's going to be the exact same thing. This bond right here has a delta En also of 0.2. And same math, same answer. Delta En here equals 0.2 as well. So this is going to tell me what the electronegativity difference is for each bond. Now you have to do each one separately. You don't like multiply by 3 or anything like that. You have to calculate it for a particular atom that is bonded to another particular atom, and you do that by finding the difference in electronegativity of those two atoms, and that will tell you what the difference in electronegativity is for that bond. So you're going to be getting answers somewhere between 0, which again, depending on which periodic table you use, you might have got for the last question, but it will start at 0. If they have the exact same electronegativities, then the difference between them has to be 0. Or it can be getting up into the 3 range. So the delta En, I should say, is going to go from 0 to 3. The difference in electronegativity of any two atoms on the periodic table will fall somewhere in this range. So you notice that if their difference in electronegativity is low, the amount that the bond is ionic is low. So essentially what we're saying is that the higher the electronegativity difference is, the more those atoms are going to be like ions. And that's saying basically the more charged they're going to be. Because if one wants the electrons more, it's going to be pulling on those electrons more, and the difference in electronegativity is going to be greater. If they both want the electrons about the same amount, then you'll end up with a low difference in electronegativity, and the atoms themselves will not be much like ions at all. If they have a high electronegativity difference, if one doesn't really want the electrons and one really does, there's going to be a high difference in electronegativity, then the atoms themselves end up being quite ionic in nature. They have a charge to them, and therefore this is what we can use to figure out what type of compound we're going to have. Do the atoms within it share their electrons really well, and therefore they don't have a big charge to them? Or do some of the atoms hog the electrons, and that therefore would make them more like ions and give us an ionic compound? Realize that this is a pretty gradual change over the course of a difference in electronegativity. There's a gradual change in the ionicness of the bonds, but as humans we like to put things in specific categories. So what we do is we say, okay, well, let's do a cutoff point somewhere in here where we can say, okay, if you're like getting over the 50% ionicness in your bonds, we're going to give you one name. And so if you're on this side of the line, we're going to say you're ionic. You're not sharing your electrons well enough, so we're going to say, okay, you're ions. And if you're on this side of the line, we're going to say, okay, well, you are sharing your electrons quite well. You've got a relatively small difference in electronegativity. So on this side, we're going to say, okay, these are molecules. And so this is how we determine which type of compound is which. We look at the nature of the bonds within them. We calculate their difference in electronegativity. If they have a large difference, we treat them as if they're going to be ions. If they have a small difference, we treat them as if they're going to be molecules. Now realize this is not a not a real categorization, right? There's going to be gray areas between the two. So we have set the line, arbitrary line in the sand at 1.7 as the difference in electronegativity. If it's over that, we call it ionic. If it's under that, we call it molecular. But if you're somewhere around there, you might be kind of ionic and kind of molecular. So there are some substances that are in the middle here, and then we leave this theoretical approach behind and we actually look at the evidence. What do these molecules look like? If their electronegativity difference is somewhere in the middle, we start looking at their properties and say, okay, well, is it acting like it's ionic or is it acting like it's molecular? So this is just a simplification, a way to identify molecules versus ionic compounds, but it is always going to fall back on what does the evidence say? What are the properties? So here's that in a bit of a summary, a little bit easier to look at. If the electronegativity falls between 0 and 1.7, it is a molecule that we're dealing with. Molecule, that says molecule. If it's over 1.7, we're talking about an ionic compound. And again, this is oversimplification. This is to make our lives easier. You can always look at the properties to say whether this is true conclusively or not. Realize that for the molecules, if they are perfectly sharing their electrons, the difference would be 0. And so we refer to them as non-polar covalent bonds, so that the bond itself is exactly evenly shared. So we can refer to that as a pure covalent bond or a non-polar covalent bond. If you're between 0 and 1.7, if you're somewhere in that range with your electronegativity difference, they're still going to be classified as sharing, but it's uneven sharing. And when we say it's uneven sharing, one's going to be differently charged than the other, or what we'll talk about is partial charge than the other, and therefore we use the word polar to describe that. If you're over 1.7, one of them so much charged than the other, we actually treat them as if they are ions, and in most of the cases they will be. So take a minute, pause here, and try this out for yourself, whatever periodic table you have. Look up the electronegativities of the atoms in here. Realize some of these have more than one bond. You have to calculate it for each bond. If it's the same math, you obviously will get the same answer. So calculate the electronegativity difference for these bonds, and then you can label the bonds. Are they above 1.7 or below 1.7? Are they ionic or are they going to be covalent? And if they're exactly equal, then you know what the answer is going to be pretty quick, and we can even call that pure covalent or non-polar covalent. There's the answers. So with hydrogen and chlorine, and again, your periodic table may differ a little bit, but it should be somewhere around 0.96 is what I got. You may have less precision as well with your electronegativity difference, but it should be somewhere around there. And therefore, this is between 0 and 1.7. So this is a covalent bond, but it's not 0. It's sort of in the middle area here. And so it is polar covalent. They're sharing, but not perfectly equally. Carbon dioxide, again, is going to be somewhere in the middle here. So they are sharing, they're covalent, but not equally. So it is called polar covalent. Bromine, whatever the number is, doesn't matter because it minus itself, or the difference between the same number, is going to be 0. So this is actually a pure covalent bond, or another name for it would be a non-polar covalent bond. Water, good one to know. This is definitely going to be a polar covalent bond. You'll notice this is pretty high. This is getting close to the almost ionic part of it. So this is definitely a polar covalent bond, and that's a relatively big number on that polar covalent bond. Methane here, a slight difference between the two, so just over 0 here. So again, they're sharing quite well, not perfect, but quite well. So it's a small polar covalent bond, not a huge difference, but a little bit of a difference. And KCl, 2.34, you're definitely over the 1.7, so we refer to this as an ionic compound. And again, if you're trying to visualize these, right, these first, what is that, 5, these are all molecules, right, because they all are below the 1.7. KCl, though, however, is ionic, so it's an ionic substance because it's over 1.7. And so if you're trying to imagine it, it is not that there is one potassium and one chlorine. That is completely wrong. Instead, there is a ratio of potassium ions to chloride ions that is a 1-to-1 ratio in this giant repeating crystal lattice structure. So again, the electronegativity difference tell us what type of compound we're dealing with. The greater the electronegativity difference, the more unequal the sharing. So once it's gone past 1.7, we say, okay, it's so unequal, we're not even going to call it sharing. We'll say it's been transferred. The electrons are actually moving from one to the other. But realize, again, as we saw with that graph earlier, it's a gradation between perfectly equal sharing and not equal sharing. So with something like lithium chloride, you have your chlorine is sort of hogging the electron. So this cloud here is sort of the electron around the atoms themselves. And so chlorine has such a high electronegativity. It's as if the electron has left lithium and is now around chlorine, and so you see the larger cloud there. And we did this when we did ionic compounds. That would give chlorine a negative charge, making it chloride, and lithium a positive charge, making it lithium ion, and we get our ionic compound. So anything over 1.7, we will imagine that this is happening. Anything under 1.7 can either be perfectly equal sharing. So again, you have one atom here, and they have their electrons around them. And so if we think of your Lewis dot diagram we did before, you got a hydrogen with an electron there, hydrogen with an electron there. They're going to share their electrons, and so we draw a bond. I mean, in reality, there's no line between the atoms, right? It is a shared area where the electrons are going to exist. And if it is equal sharing, we say it's a covalent bond or a pure covalent bond, or sometimes called a non-polar covalent bond, but perfectly equal sharing. If, like with HCl, we have a chlorine and a hydrogen, the difference between them isn't huge. It's not over 1.7, but the chlorine still is hogging the electrons. You can see that it is got the electron from hydrogen spending more time around the chlorine. I won't draw an arrow though, actually, because it hasn't actually taken the electron. It is not ionic. It is still covalent, but since chlorine has a high electronegativity, the difference is getting close to 1.7. It's getting up there. It's quite a bit larger than 0. It is a polar covalent bond that we have here. It is a sharing of electrons, but an unequal sharing. That's what polar means, is you've got these differences. And we use this little symbol here. This is a lowercase delta. And it is saying that chlorine here has a negative charge, but it's not an ionic charge like it has in lithium chloride. This one here it's not taking the electron away from the hydrogen. It is just hogging the electron. And so we put this lowercase delta sign to represent a partial charge. So that sort of kind of looks like a curvy looking D or an S or something like that with a negative. That means it is a partially charged. It's not an ion yet. It's a partially charged atom. It is hogging the electron. So they are still, if we're drawing our Lewis structure, they would still have a line between them representing the bond, but they are partially charged. Hydrogen has its electrons being pulled away from it, and so it is partially positively charged. So see if you can try this out where you're actually drawing the Lewis structure, then showing the bonds, and then writing in those partial charges that we saw in the last one. So take a pause here and see if you can do it for carbon and fluorine. All right, should do the math first so we know what sort of bond we're drawing. Notice that this is less than 1.7, therefore it is not ionic, it is covalent, and it is not 0, so it is actually polar covalent. It's getting on the high side of polar covalent, so quite polar covalent. So we have our polar covalent here. We have these partial charges, and whichever one has the larger number, it's the one that's going to hog the larger electronegativity number. It's the one that's going to hog the electrons. So here, fluorine has the electronegativity somewhere around 4. It's going to be hogging the electrons away from the carbon. So when we go to draw this, again, carbon is in group number 14, has 4 valence electrons. Fluorine is in group number 17, it has 7 valence electrons. So we start off with that. They're going to want to share a pair of electrons. That'll make fluorine happy. And of course, we don't draw the circle and the dots. We draw instead a single line representing that shared pair of electrons. That makes the fluorine happy. The carbon is not, however. So as you'd imagine, hopefully you can start seeing these in your head without having to draw every aspect of it. You're going to need another fluorine to share a pair there with carbon. But again, we replace that and draw a line. So the same thing is going to happen with another fluorine and another fluorine. So as you'd imagine, it takes 4 fluorines to bond with carbon, and we end up with our formula CF4. So our carbon tetrafluoride, this is our molecule, and I know it's a bond. I know it's a covalent bond. I should be drawing these lines in here because the electronegativity difference is less than 1.7. So I draw lines. Now I can include the partial charges. I can say, okay, well, yes, they're sharing this pair of electrons, but fluorine is hogging it. So fluorine is going to end up with a partially negative charge. That's that lowercase delta. That's not a very good one. And this carbon is going to have a partially positive charge to it. Now that is for every single bond, each one of the bonds. And again, feel free to do this calculation 4 times if you like. It's going to give you the same answer each time. For the electronegativity difference of each of these bonds is 1.43. So each of these is a polar covalent bond, and each of them have these partial charges. So this fluorine would have a partially negative charge. This fluorine would have a partially negative charge. Let me get this one. There we go. That's better. That fluorine has a partially negative charge as well. And then the carbon would have a partially positive charge for each of those bonds. I'm just going to draw it once because it applies to all 4 of those bonds. So the trend for electronegativity, as we saw with when we actually saw the numbers of them, is that it increases up and to the right. And so we see with fluorine, the electronegativity is really high. Now be careful with the noble gases, right? Remember the definition of electronegativity? This is the ability to track electrons within a bond, and those noble gases do not like to form bonds. Now, that's not entirely true. You can get some bonds out of the larger ones, but essentially most of your periodic table will probably give you no electronegativity value, at least for the first 3 noble gases, and you're probably not going to do any bonding with the other ones, so you can ignore them for electronegativity, essentially. But other than those noble gases, it increases up and to the right, making fluorine the most electronegative element on the periodic table, and then again decreasing as you move down and to the left. It's going to be less and less. So again, you should be able to explain why this trend is, which is a whole lot easier than trying to memorize the trends. If you understand that, again, it's all about the effective nuclear charge. It's all about the attraction of those electrons to the protons. And for the same reason we see the trend with ionization energy and atomic radii, it would also cause the exact same consequences for electronegativity. If they have a stronger pull on electrons, when you put them in a bond, they're going to pull on their partner's electrons strongly as well. So as you move from left to right across a period, for the same reason, you're getting more protons pulling on the same electron shell. You get a higher effective nuclear charge. The electronegativity will increase. As you move up a group, again, you're getting fewer inner shells. You're going to have more attraction for those other electrons that are there, the outer electrons, for the nucleus, and therefore you're going to have a stronger attraction as well. And again, higher effective nuclear charge that also will attract the electrons in other atoms as well, so therefore increasing the electronegativity as well.